Okay, so here in podcast 5.1, we're going to be talking about how to draw the Lewis dot structures of covalent compounds, which is really going to be the foundation of the rest of this unit. So it's a really important idea to get down. If you have any questions, we're really just covering page 1, but there's a couple different variations in what we're doing here. If you get lost anywhere, stick with it, take the rest of the notes, but please make notes, question marks, post-its, whatever you need in order to ask about what you don't understand so that I can explain it better one-on-one when I see it again. So page 1 at the top starts by giving you these 6 steps for how to draw covalent structures. And it's really not this complicated, but it's important that we follow this exact process, even if we start to kind of combine some of these steps together. And the first step is to count the total valence electrons from all of the atoms in the compound. Now, if you remember, the periodic table tells us how many valence electrons each atom has. It really just comes back to what column the element is in on the periodic table, all the way from the alkali metals, which are the first column that have 1 valence electron, all the way over to the noble gases in the last column that have 8 valence electrons. Remember, we have to skip over those transition metal d-block elements because we can't really predict very well how many valence electrons they'll have and what charges they'll end up with, and plus they're metals anyway, so we won't need that much for our covalent compounds. And honestly, we won't be using the noble gases very much either because they don't tend to form bonds, so we really just need that little boron through fluorine columns right there. But let's get back to the packet type problems. What we're doing here is adding up the number of valence electrons in a compound, like CH4. That's going to be the very first example that we do. So we're going to be finding C and H on the periodic table, and H is in the 1 column, C is in the 4 column. So we're going to be adding up 4 valence electrons from carbon and 1 from H, except remember that that is CH4, telling us that there's 4 hydrogens there. So we're actually going to be adding in 1 valence electrons from each of those 4 hydrogens, which gives us a total of 8 valence electrons for this structure. So that's what we're going to be doing with these valence electron numbers. Now, after we have done that, and kind of consider these next 2 steps as a single step, we're going to kind of decide on the basic structure of our covalent Lewis dot and put the least electronegative element in the center and connect the outer atoms to the central atom with a single bond. Everything's got to be connected in order to be a molecule. Now, the one exception to putting the least electronegative element in the center is hydrogen. Hydrogen is never in the center. When it comes down to it, though, you're never going to have to kind of think about this too hard, because even in things like CH4, not having looked at the periodic table already, if there's only 1 C and 4 H's, then C is going to have to be the central atom, because we can't just have one of the H's in the central atom. Nature likes symmetry. So that's going to be what our decision process is like. We're not really going to have to think back on which is the most or least electronegative. So we're just going to start the basic connections, getting things arranged and single bonded together. Now that single line that we're going to draw as our single bond actually represents 2 shared electrons. That's going to be important because after we draw our bonds, we're going to be trying to add our remaining electrons around the rest of our molecule as lone pairs. And so we need to know how many we have left. So generally, after I draw my bonds, I subtract from the actual number of valence electrons that we started with to figure out how many electrons I have to put out as lone pairs. Now, these lone pairs are just 2 dots, kind of look like this semicolon here, and those 2 dots do represent 2 shared electrons. So we're always putting our electrons in pairs. You're never going to be drawing any single dots at a single time anymore. And really, at this point, you've done everything you need to do. You're just going to keep adding lone pairs until all of our atoms are happy and full of electrons. Now, for most of them, that means that they want 8 valence electrons around them. That is that octet rule thing that we had talked about and learned about. But one very important exception to be aware of is hydrogen only needs 2 valence electrons, and we're going to be working with hydrogen a lot. There are some other exceptions that we're going to see and talk about later on down the page, but those are going to be kind of the minority, not the rule. So we're just going to keep going until all of our atoms are happy and full with however many electrons that they need. And here, that last step, step 6, is really just double checking the work you've already done. We want to make sure we've used all the electrons from that first step and all our atoms are happy. So really it just comes back to counting what you got, using what you got, and being confident enough to know when all of these kind of important steps have been met. So let's get to our first problem. You can see up there in the title bar, I've already kind of simplified this down a little bit into 3 steps. And I'm going to kind of help walk you through using less and less in order to be able to get to the same place. So step 1 is count our electrons, and we've already done this just by finding these atoms in the periodic table earlier. We know we have 8 valence electrons to work with. Now we have to start arranging things, and like I already kind of used as an example, C is going to be in the middle of these 4 H's, and it will help you in general if you line these up at 90-degree angles, and you'll kind of see why as we do more and more examples. But now that I've got my atoms arranged, I'm going to single bond these atoms together with a single line between each of them. Since those lines represent 2 shared electrons each, and I have just drawn 4 of them, that means that I have just used all 8 electrons that I had to work with. And if I go back through and check, my carbon has 4 bonds around it, so that means that it has 8 electrons around it in its kind of area, so it's happy. And each of my hydrogens has a single line to it. And remember, hydrogen just wants 2 electrons, so it's happy with that single line to it. That's all that it ever really wants. If you ever start adding dots around hydrogens, you know you're doing something wrong. They're happy just being included, just with a single bond, 2 electrons, that's all they need. So all of my atoms are happy, all my electrons have been used. This is my correct final structure for CH4. That's all we really got to do. They do get a little more complicated, but that's the basics. So let's look at H2O. We see our friend H again, hydrogen, each bringing 1 valence electron with it, and oxygen brings 6. So this time we have 8 valence electrons to work with again. We're going to put our oxygen in the center because it's this only one that can be the central atom. H's never can be, and plus they'd fight over it anyway. Single bond between the O and each of my H's. This time I've only used 4 out of my 8 electrons. So now it's time to add my remaining 4 electrons as lone pairs. Now I know I've said to generally start with the outer atoms here, but my outer atoms are hydrogens. I don't need any valence electrons. They're happy. So I can feel confident adding my valence electrons as 2 lone pairs around my oxygen. And this is one of those times when I'm going to point out how nice it is to work in right angles. I could be sloppy about this and still probably give you credit for things, but if I work at these right angles, then I know that my oxygen is full when all 4 of my sides have either a line or a lone pair on it. Once all 4 of my sides are kind of full with an electron group, electron pair, then I know I've got to 8. So it just really helps visually and keeps things neat for you and me. Now, NH3, 5 valence electrons come from my N, 1 each from my hydrogens, gives me 8 again. Don't get used to that being a thing. It won't always be. Still keeping things at right angles because that helps so much. Single bonds to each of my N's. I've used 6 out of my 8 electrons. So hopefully it's a little bit obvious that the N is all that needs electrons. It had that nice open top spot ready and waiting for them, so I put my lone pair there. Now I've used my 8 electrons. All my atoms are happy, and that structure is done. Now our SO4, -2, is going to get things a little bit more interesting really quickly. We've got 2 special things going on. First off, this is a lot bigger. Even before I get to that -2, my number of electrons is going to be rather large because each of those O's brings 6 and so does the S. So we've already got 30 electrons just from those 5 atoms there, SO4. And then this -2, which scares people a lot, that's just an extra 2 electrons on top of the other electrons that S and O's brought with them. So it's just another couple of electrons to work with because it helps to stabilize this molecule. So don't get too worked up about it. It just makes your numbers you're working with a little bit bigger. And these are already pretty big to start with, I know, but it's really not that bad. Once you follow our process, it follows through very nice and easy. So we've counted our electrons. Let's start arranging things. S is going to have to go in the middle because it's the only single atom we've got. I can be a little bit neater with my O's. And now I'm going to single bond each of them to that central S. And that is 8 out of my 32 electrons. I am definitely nowhere close to done. So I'm going to start adding lone pairs around my outer atoms, my oxygens, until they get full. Once again, right angles are really helping me because I can see just adding those 6 electrons, that's 3 lone pairs around the oxygen, has gotten it full. I'm at 14 electrons now. This brings me up to 16, 18, 20, 22, 24, 26, 28, 30, 32. And now maybe you understand why this SO4 really wanted to have an extra 2 electrons, because it just works out so nicely for that to create a nice single bonded structure where everything has the 8 electrons that it needs. And the last thing you need to do with any ion that has a charge on it, and it starts with a charge on it, so it's not trying to hide it. If it starts with a charge, put that charge on your final structure and just make sure anyone else looking at that would just see SO4, would think you've cheated because you have more than 30 electrons there. So just kind of puts it in context. Square brackets with the charge on the outside anytime you have an ion. So what if this doesn't work out perfectly? What if I ran out of electrons before all of the atoms have what they need? It could happen. Well, what we're going to do is force the electrons to share more. It says to make an additional bond to the central atom. And really what we're going to do is take electrons, or force an atom that has all the electrons that it needs to share some of those electrons with the atoms that don't have what they need. We're not really taking them away from that atom. We're just going to force it to share more by making an additional bond, a double bond or a triple bond, instead of this single bond, single line that we've been talking about. So larger atoms are more likely to form, but you don't have to be looking out for specific types of atoms to make these form. The electrons are really going to tell you when this happens. If you run out of electrons, but not all our atoms are happy, that's when we need to make a double bond or a triple bond. Now, just some information about these. Of course, our double bond has more energy. Holding together our atoms is a stronger bond. Triple is even stronger. But because it's stronger, they're being held really, really tightly. Our single bond is actually the largest, longest bond. The tighter it's held, the more energy holding our atoms together, the closer they are pulled towards each other. So if you have a model kit to play around with, or if you mess around with one of mine here in class, then the triple bonds are going to end up being the shorter bonds, not the longer ones. So let's see some of this in action. I have the same 3 steps up there above, but just a little side note. If I run out of electrons, turn some pairs into a bond. So let's start by counting up the electrons from these 2 oxygens. 6 plus 6 means 12. I don't exactly have a central atom here since there's just 2 O's, but that's kind of neither here nor there. We just need to connect the 2 O's together. So I've used 2 out of my 12 electrons. Okay, I'm going to make them a different color here in order to make them stand out. Let's add the rest of them. So that's 4, 6, 8, 10, 12. Well, that's unfortunate. We don't have 14 electrons in order to make this full and completely happy. So I might go and double check my count, but no, I'm for sure that's just 12 electrons to work with, and this is 12 already out here. So I've ran out of electrons, but not all my atoms are happy. What I'm going to do is take some electrons from my happy oxygen, the one that is full with all the electrons that it could want, and instead of letting it keep those electrons all to itself, we're going to make it share them as an additional bond between these oxygens. So now that those have moved, I can erase them from where they came from. And if you double check, I've used 2, 4, 6, 8, 10, 12 electrons still. But around each of my oxygens, I've got 2, 4, 6, 8, and 2, 4, 6, 8. So all of my atoms are happy and full, and I've used only the electrons that I've got. So this is our double bonded O oxygen molecule that we had to make because we ran out of electrons. That's all there was to it. In our next example with N2, they each have 5 valence electrons that they bring. So here we're going to feel extra short because if I single bond my ends to each other here, then that's 2, 4, 6, 8, 10. Ran out of electrons, and I'm missing a lot of electrons here around this N, so I'm going to take some from the N that is all nice, full, and happy. So make those a double bond. Now I still have only used 10 electrons, and this nitrogen over here is still happy, 2, 4, 6, 8 around it, but this one still only has 2, 4, 6 around it. So it's not quite done, it's not quite happy, and I haven't done anything wrong. It's better off than it was before. I just need to do it again. So I'm going to take another pair of electrons and make this into a triple bond. And now, still with only using 10 electrons, I now have 2, 4, 6, 8 electrons around each of my nitrogens here. So, triple bond in a very common daily molecule all around us, N2. Now, it's not just in diatomic molecules that we have multiple bonds. Something else, CO2, very common molecule. C brings 4 electrons to the table. Each of those oxygens brings 6. So we have 16 to work with. Carbon is going to be in the center with a single bond to each of my oxygens. I only used 4 electrons out of my 16. So if I keep adding, this is one of those times where it really does pay to put them around the outer atoms. It makes it a lot easier to get things even if we can always share into the center atom. If it isn't happy, instead of having to share from one side of the atom all the way to the other. You'll see what I mean if you try it. So that's 6, 8, 10, 12, 14, 16. So here is all 16 electrons, but while my oxygens are each happy and full with 8 electrons, my carbon in the middle just feels like it has 4. So I'm going to take a set of electrons from one oxygen, turn them into a double bond instead. Now my carbon's a little closer to being happier, but not quite. And let's go ahead and keep things even. Take a pair of electrons from my other oxygen and move them into being a double bond here. And now I can confirm again, 2, 4, 6, 8, 10, 12, 14, 16 electrons is all that I've used. And every atom has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8 around it. So I am done with my CO2 structure here. So double bonds don't have to be scary. It's really weird when you run out, but when in doubt, double count to make sure you counted your electrons right. Double count to make sure you've counted the electrons you've drawn already. But if those things are correct and you're confident in them and they don't match, that's when you're going to have to make a double bond. So we've talked about these already. There are some exceptions to the octet rule, more than just the hydrogen example that just wants 2, where they don't need 8 to be happy. And these structures are pretty simple. You just have to remember that you don't need to make double bonds with some of these special elements because they are happy already and they don't need those extra electrons, that extra sharing. So boron is probably the next most likely one for you to see other than hydrogen, which, like we've already said, only needs 2. Technically, aluminum and beryllium only need 6 and 4 respectively, but seeing as these are metals, these are not as common to see in covalent compounds. They do have very low electronegativities, so they can technically form some very low electronegativity difference, technically covalent compounds, but those aren't going to be our focus here because in all technicality, they are ionic. They are metal and non-metal. Now, there's also a lot of atoms, mostly sp, are going to be the ones that you see, and there are others in the 3rd energy level or above that can actually fit more than 8 electrons if needed. And you saw some of these already in your last unit when we were naming things like sulfur pentafluoride. Well, think about it. If sulfur has 5 fluorines bonded to it, then it's going to have more than 8 electrons just from those bonds there. So these things can happen. This isn't really our focus here in honors chemistry in kind of year 1 chemistry. If you take AP chemistry with me or anywhere college chemistry, then you'll get into more of those exceptions and special cases. But just be aware that it can happen. I want to show you a couple examples here. BeI2, if I were counting up these electrons, Be brings 1. Each of those I's brings 7. So that is 16 electrons to work with. Be is going to go in the center. Our I's around the outside. And then a single bond between each of them is 4 of our 16 electrons. So 6, 8, 10, 12, 14, 16, and we're actually done. It might seem like one of those cases where I ran out before my beryllium is happy, but remember what we were just saying, is that beryllium is happy with just 4 electrons, and it got those just from these 2 bonds here. So we're done. Next we see boron trichloride here, and if boron brings 3 valence electrons and each of those chlorines brings 7, we have 24 electrons to work with. Boron is going to go in the middle with 3 chlorines around the outside, connected all together. That's 6 electrons, and that's all boron really needed around it. So I can add the rest of those 24 electrons around my chlorines. Now I've only used 24. Everyone is in fact full and happy. So with P of 5, there are 5 valence electrons from P and 7 from each of the fluorines, which gives us a total of 40 valence electrons to work with. I'm not going to be able to make things at nice right angles here, but it doesn't really matter because my P is going to end up with more than 8 valence electrons anyway. And we can see that as soon as I add my 5 bonds to it, that it has 10 valence electrons around it. But it can handle that. Let's just keep going. My first fluorine to be full is going to need 6 more electrons, so that's now at 16. 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. So that is all my electrons, and all of my atoms are in fact happy and full. It's not that phosphorus needs more than 8 to be happy, it's that it can handle more than 8 and still be happy there. So that's it for now. I will go over the resonance section with you in class and any other things that you have questions about from this first section.